Hey everybody, sorry for my tardiness. I lost track of time for a second, but oops, and I almost just ended the meeting. Let me chat here and myself. Oh. Here is the. Sorry, there's a million things on my screen. Not everything is where it needs to be. Okay, here is the. Fill that out when you have a second. Also, I don't know if you guys can hear it, but there is definitely still lots of noise going on outside, so I will try to tune it out as best I can. But I did not do an excellent job of that last Friday. Let's see, there was something else I had to say. Good question. Let me check. You know what? I will look, Jennifer, I will look at that and see, and let me write myself a little bit here. And I will follow up on that and see if I can find it. I don't know if, let me actually, well, let me look at the website while I'm at it. Let's see here. Sorry, this is a good question. I'm wondering if there, yeah, the pre and co-classes are available. Oh, but I don't think, oh yeah, they're there. Okay. It's possible that we're not offering co-stats in the fall because it's something that in the fall we have so many other classes that we are kind of set to teach that I don't think we are doing co-stats in the fall. That said, Jennifer, I'm certainly available during the fall, and not that I showed you guys last Friday that I was good at it, but I can help with statistics generally. So I don't think we have a co-stats class. I'll double check with Sarah to be sure about that. But I and Sarah are also available and able to help with statistics. So let's see here. Oh, there was something else I feel like. Sorry, 1 minute. One other thing. There we are. Sorry, I'm just pulling up all the stuff. Okay. So it looks like, yeah. It looks like Rodriguez hasn't quite given any homework yet about probability stuff, which is fine. I was going to do some probability examples, and I will try to I've got lots of sources here with questions that I think are good. So I think we should just jump right into that. If you guys want to see some non-probability things though, feel free to ask. We can do whatever you guys want. I'm just trying to start somewhere. But if there's a specific homework question you guys want me to look at, I can also do that. Maybe there's not. Sorry, it's so loud out there. And it really kind of is variable. They're like, sometimes they're doing stuff, sometimes it's quiet. So let's look at some examples here. And I'm going to try and do some, what I think of as basic examples, because they're probably not, but it's hard for me to remember that things are not always super easy. So let's look at this example here. 2 marbles are drawn at random without replacement from a box with 2 blue and 3 red. So I've got 2 blue marbles and 3 red marbles. And so we want to ask some questions like, well, first, I mean, it's kind of good to list out what can happen. So, I mean, and there's kind of, there's a couple of different ways to think about what can happen here. So overall, there's kind of like three things that can happen. You can get 2 blue marbles, you can get 2 red marbles, or you can get a blue and a red marble. So there are 3 kind of different things. But if we want to list out kind of all of the sample things, well, we have to think of these blue marbles and these red marbles all being different, right? This is the first blue marble, second blue marble. This is the first red marble, second red marble, third red marble. And so if I'm trying to think about what can happen, well, I pick one thing, right? So I pick a blue or a red marble. And then I pick one of the other ones after that. And if I'm just trying to think about how many different things can happen, well, there are 5 choose 2 ways of picking marbles, which is 5 factorial over 2 factorial times 5 minus 2 factorial, which is just going to be 5 times 4 over 2, which is 10. And we can even list them out, right? I can either have the first blue and the first red, or the second blue and the first red, or I'm kind of doing this backwards, with the first blue. And so I'm kind of thinking of, wow, this pen is dying. And, oops, that should be 3. So those are 6 of the things that can happen. And then, yeah. Sorry, the noise is just killing me. I don't know. I feel like I've listed too many things here. Have I? Sorry. Oh yeah, sorry. I'm trying to say like order matters and order doesn't matter. I'm sorry. And then we could have 2 blues or 2 reds, right? So these are all the ways you could pick 2 balls. You have one of the blue ones and one of the red ones, and these are different ways you could get that. Or both blue, or both red. And there's 3 different ways you can get both red, because you can pick these 2 red ones, or these 2 red ones, or these 2 red ones. So then we can add, and the reason it's kind of important to list out all the things that can happen is so you can answer questions about probability. Because someone could ask, something like, what's the probability that 2 blue marbles are drawn? Well, if we hadn't listed all these out, we might think it's something like 1/3 or 1/4. Because you might think, well, it can either be both blue, both red, or one of each. And if you were thinking that they were kind of all equal probability, you would end up making an error. But here we can see, well, and I should say I should make more blanket statement here. If you're asking about a probability of something happening, the way we typically calculate it is it's the number of ways the thing you want to happen can happen, divided by the total number of things that can happen. So here, if I think about the total number, or the probability of 2 blue marbles being drawn, well, there's exactly one way that can happen. The first one is blue and the second one is blue, divided by the 10 different other total things that can happen. I should point out, I might have made my list only half as big as it needed to be, right? It would probably also be accurate to list all of the flips as well, to list the red one, the blue one, and the red one, blue two, and all of these other ones flipped, and this one flipped, and this one flipped, and this one flipped. So that would double the number of things, but it would also double the number of ways each thing can happen. So it's you could also think of this as probably being 2/20, which is the same thing. So let me ask you guys, and what's the probability of getting 2 red marbles? Well, how many ways can we get 2 red marbles? Looks like there's 3 ways to get that. The probability here would be 3 out of 10, or 6 out of 20. And then you could, for the last one, count it up and say, well, what's the probability of 1 red and 1 blue? You could say, well, 1, 2, 3, 4, 5, 6 out of 10. But we could also use what's called the complement rule. Right? If we know this is the only thing left, right? We found all the other things that can happen. Probability of both blue is 1/10. Probability of both red is 3/10. The only other thing can happen is 1 red and 1 blue. So the probability has to be whatever's left over from 100% or 1. So instead of doing it as 6 over 10, I'm going to say, well, it's 1 minus those other probabilities, which is 1 minus 4/10, which is 6/10. So when you're talking about like an event that happens and the probability of different things happening, all of the probabilities have to add up to 1 or 100%. And we often use that to our advantage to figure something else out. In fact, there's a really good example of this. Let's say we flip some coins. Has he done a coin flipping example in class? No? Yes? Maybe? Are you guys like, we're not in his class? Okay, let's say we flip 3 coins. The reason I asked is because 3 is kind of the typical example, and so if he'd already done it, I was going to do a different number. And I want to say, record the number of heads. And by extension, also tails. How many ways, or I really should say, what's the probability of flipping exactly 2 heads? Well, here's the thing, right? There's a lot of ways that you can get 2 heads. So what we're going to do is we're going to list them all out. So you can have all heads, or you can have 2 heads and 1 tail. So you can have heads, heads, tails, or heads, tails, heads, or tails, heads, heads. Or you can have 2 tails, 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 heads, tails, heads, tails, heads, tails, tails. And finally, you could have 3 tails. So it looks like there's exactly 3 ways of getting 2 heads out of 8 ways total. So here the probability of 2 heads, apologies, is equal to 3 out of 8. I mean, actually, this is a specific kind of example. The way you can actually calculate this is say, well, it's the number of ways of choosing 2 heads, right? Right, there's exactly 3 ways of getting 2 heads. 3 choose 2 of the coins or heads, times the probability that those two coins flip to be heads, well, the probability of flipping to be a head is 1/2. So it's going to be 1/2 times 1/2, which is 1/2 squared, times the probability that the other coin is a tail, which is also 1/2 to the first. So this is how you could calculate this without having to list everything out. It's not so bad when you're flipping 3 coins. It's terrible if you're flipping 10 coins. Right? If I was going to flip 10 coins, there's 1,024 possibilities. And I don't want to have to list them all to know what's going on. So in fact, actually, before we go there, the other kind of question you could ask here is, what's the probability of flipping at least one head? And although here you could certainly count them up, right? There's 1, 2, 3, 4, 5, 6, 7 ways of getting one head or more. You could also say, well, the probability of getting at least one head is just everything except for the probability of getting no heads. So this is exactly equal to 1 minus the probability of 0 heads, which is, again, an example of using the complement. And so that's going to be 1 minus 1/8, which is 7/8. So that's another way you could do this. So let's, sorry. So let's kind of extend this example to more coins, because I think it is something that could be asked about. So let's say now we're flipping 10 coins. I'm going to ask similar questions. So what's the probability that the number of heads is equal to, let's make it 6. Okay. This is not something you can do by, not you can do by hand. This is not something you can do without knowing how things work. So there's a lot of ways you could pick 6 of the coins to be heads. In fact, there are literally 10 choose 6 ways of picking 6 of the 10 coins to be heads. And that's going to be, so when I see this, I don't really actually write out 10 factorial over 6 factorial times 4 factorial. Like, I know that's what the formula is, but what I'm actually thinking of is, well, okay, the 10 factorial and the 6 factorial cancel a bunch of stuff, and I get 10 times 9 times 8 times 7, and then the 6 factorial cancels with the 6 factorial down there, and then I got this 4 factorial here. So those just cancel out. That's kind of what I do right off the bat, just because I know that's going to happen. You could also use a calculator, right? Like, I'm doing it kind of a long way. There are buttons for this on your calculator, right? I showed you guys the button. Okay. So, right, and then this would be 4, right? Stuff should always cancel. So like 4 and 2 cancel with the 8. 9 divided by 3 is 3. So I get 10 times 3 times 7, which is 210. So that's the number of ways I could pick a heads. So in this particular example, you can totally just say it's that divided by the total number of things that can happen. But that's because the probability happens to be split down the middle, right? If you had an unbalanced coin, it wouldn't be okay to do it. So what I want to say is right now is that it's 210 divided by, that doesn't look like 2. Divided by 2 to the 10th. Because there's 2 to the 10th total possibilities, right? Each coin could be a head or a tail. So it's 2 times 2 times 2 times 2 times, right? That many things. Which is 210 out of 1,024. And that works totally fine in this case where the probability of getting a head or a tail is the same. But the reason what we're actually calculating here is the number of ways to get 6 heads times the probability of getting a head times the probability of getting 6 heads times the probability of getting 4 nut heads, which is 4 tails. On the other hand, if I had an unfair coin with a probability of getting a head being, say, 2/3, and the probability of a tail 1/3, then even though the number of different ways you can get 6 heads is still the same, right? There's still 10 choose 6 ways of picking 6 heads out of the 10 coin flips. The probability isn't going to be 210 out of 1024 because you're more likely to get a coin flip being a head. So this probability of the number of heads equaling 6 would be the same as this formula here. It'd be 10 choose 6 times 2/3 to the 6th times 1/3 to the 4th. This is what's called a binomial probability. So the other thing I want to say here is, just like in the previous one, we could ask a question that is seemingly challenging, like, what's the probability of at least 2 heads? So even with knowing this formula, and I'm talking about the fair case now. I'm back in the fair case, not the unfair case. Even with this formula, that knowing the probability of getting the number of heads being a certain number is 10 choose that number times 1/2 of the number times 1/2 of the other number. It's still a lot of calculating. So you have to do it for 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? I don't want to do this thing 9 times. And I don't have to. Because I can say, well, that's going to be 1 minus the probability of the number of heads being less than or equal to 1. So really it's just the probability of 1 head or 0 heads. Which isn't so bad. It's going to be 1 minus, okay, the probability of getting 0 heads, well, let's calculate that over here. Probability of 0 heads is 10 choose 0. So there's exactly one way of getting 0 heads, all tails. By the way, I do think this is a good example of how choosing 0 makes sense. Right? Like sometimes when you say, like, how many ways can you pick 0 things out of this many? And it's kind of like, well, that seems odd that it's 1. Right? There's one way of not picking it. But here it really makes sense. There's one way of picking 0 heads because you're picking all tails. Times 1/2 the 0, right? Because you pick 0 heads and then 1/2 of the 10. Which just ends up being 1 times 1 times 1/2 of the 10th. Or 1/2 to the 10th. And then the probability of getting 1 head is 10 choose 1 times 1/2 to the 1 times 1/2 to the 9. Because there's 10 choose 1, which is exactly 10 ways of getting 1 head. The first one to head, the second one to head, the third one to head. So that's going to be 10 out of 10. So then calculating this, it would be 1 minus these two numbers. Which you could leave as is, or you could say, well, it's 1 minus 11 over 2 to the 10th, which is 2 to the 10th is 1,024. So it's 1,024 minus 11. So pretty good chance of getting 2 or more heads, right? Which would make sense. If you're flipping 10 coins, you're pretty confident you're probably going to get at least 2 heads. So like it's like a 99% probability. All right, let's look at some other questions or some other ideas. This is problem 6 from your textbook. Seems like a good one. Computer password is 7 characters in length. How many passwords are possible? If all the characters are lowercase letters. All right, so you have to be a little bit careful, I feel like, thinking about this. So I kind of like to write things out. So like, I got 7 spots. My only restriction is that they're all lowercase letters. It can't be numbers, it can't be uppercase, it can't be other weird things. But I've been told nothing about repetition, right? I could make my password AAAAA if I wanted. So to me that says I've got 26 choices here, 26 choices here, 26 choices in each spot. So that's how I'm seeing this one, right? There's no restriction on the repetition. So B, what if we now allow lowercase and numbers, but they all have to be different. Which I know is kind of a weird condition for a password. And most passwords don't say every letter has to be different than every other one, right? There's some other restrictions usually, but not like you can't use the letter J twice. So here, I'm thinking about this the same sort of way. So how many choices do I have for my first spot? If I'm now using all the lowercase letters and the numbers. Number that's going to come up with a lot, actually. 36, right? There's 26 letters, there's 10 numbers. But then since we're in the situation where we can't repeat anything, the next spot there's only 35 choices. And the next one there's only 34 choices, and 33, and 32, and 31, and 30. If I was trying to write this in a concise way, I would probably write this as 36 factorial over 29 factorial, because that seems like the easiest way to write it. Some people would probably also write this as 36p29. It's the number of p7. Sorry, I always screw that up. It's the number of permutations when you pick 7 things out of 36 things, with the things having to be distinct. Or we're picking 7 different things. Let's see, where'd you go? Okay. Let me give you guys the attendance again just to make sure everybody got it. Let's see here. So I posted a quiz that had a 2 fair dice question. I guess I could change it to make it less sure. Let's say 2 fair dice. Let's say 2 fair 4-sided dice. What's the probability that the sum of the dice is I don't know, 4. It's 4. Yeah, well, at least for now, it's probably a good idea to list all the things that can happen. So normally I wouldn't probably list everything. But when you're first seeing it, it's probably a good idea. Now let me ask you guys a different question. How many different things do we think can happen if I'm throwing 2 dice that each have 4 possible outcomes? Exactly. 4 times 4, 16. 4 options for the first die, 4 options for the second die. Sometimes people maybe get a little bit thrown because they start thinking about, like, is a 1-5 different than a 5-1? 5 is not an option here because it's a 4-sided die. Is a 3-1 different than a 1-3? And the answer is yes. And to help you kind of keep track of that, I often think of the dice as being different colored. So like one die can be red and one die can be green, and then right, different things can happen. So I'm going to make a little table here with all the things that can happen. Again, after some practice, you probably don't need this. So the green die can be 1, 2, 3, or 4. And the red die can be 1, 2, 3, or 4. And then we're just going to write out what you get. So here I'm getting, so I can do this smartly. Probably not. A 1 and a 1. Here you're getting a 1. Oh, it's just, yeah, I can do it smartly. And here I'm getting a 2. Let's be real smart, James. I figured it out. I got kind of smart. And then the green die is a 1. I've made this table more times than you would maybe think, and I've never actually done it this way before, where I've listed all the, like, it seems like the best way to do it for sure. So these are all the things that can happen. All 16 of them. Okay, so now we can look and see how many ways are there of the total being a 4. Well, there's 1 right here where I roll a 1 and a 3, a 2 and a 2, and a 3 and a 1. So there's 3 ways out of 16 ways total. This is kind of, actually, you know what, this is kind of neat. So let me ask you guys another question. What's the probability that the sum is even? Well, how many ways are there being an even thing? Let's see, there's this one here. So something that you'll see if you look at this long enough is that the diagonals going from upper right to lower left always have the same sum, right? So this diagonal sums to 2, this diagonal adds up to 3, this diagonal, all things add up to 4, 5, 6, 7, 8. And it's true if they're 6-sided dice or whatever, that's always how it works if you make your table like this. So I can see that there's 1, 2, 3, 4, 5, 6, 7, 8 different ways of it being even. And this is kind of a thing that I've encountered because sometimes if you play like games with people, you say, let's roll dice to see who goes first, and sometimes you tie, which is annoying, but fine. But you can also do this. Instead, you can say, well, to decide who goes first, to call whether it's going to be odd. It's kind of like flipping a coin saying heads or tails. Call whether it's going to be even or odd, and it's always a 50% chance, which is kind of neat. It's always a 50% chance if you're rolling dice with an even number of sides. If you happen to have an odd number of side dice, which I don't think is a thing that really exists, but pretend like it could, then it would not be this case because then you would have an odd number of things. But yeah. So yeah. Anyway, so you could roll like 5 6-sided dice. Be like, odd or even, and the probability of getting odd or even is the same. It's 1/2. It's kind of cool. We can also ask questions like, so I kind of change that to say, what's the probability that the product of the dice is greater than or equal to 7? Which is a totally different question. So if I was doing that, I would probably just start marking things off. I'd probably like, okay, well, let's see. No, it's not working. Trash bins here. Sure. So let's see. This one definitely multiplies to more than 7. None of them actually multiply to 7, by the way, right? So if I was going to say greater than or equal to 7, it would be equivalent to saying that the product is greater than or equal to 8, right? Because 7 isn't an option. This we have man, pen on the finger. Okay, so let's see. So we want this one. This one's 8, 12. This one's 12. This one's 8. This one's 8. This one's 9. And that's actually it. So it's 1, 2, 3, 4, 5, 6 out of 16. Which in this particular example happens to be the same as the probability of the sum being greater than or equal to 6, right? Because the sum of these is all 6, 7, and 8. It's kind of neat. Let's see. Okay, we've talked about dice a little bit. We've talked about I suppose we should roll back around to playing cards. Yeah. Okay. Okay, so the usual 52 card deck. Oh, I was going to look for some hands and I totally forgot to do that. Sorry, guys, I'm writing myself in notes. So I actually maybe remember to do the thing. I think it's in my scribbles over. Yeah, Sarah. Yeah, I see the one hand up there, but sorry. Maybe I'll actually remember to do it this time. So let's say we draw 2 cards without replacement. What's the probability that they're the same suit? Okay, well, again, this is and most of these are usually how many ways can we get the thing we want divided by how many ways can you get the total number of things. So first of all, what's the total number of ways of drawing 2 cards without replacement? What seems like a logical answer? That's probably right. Well, here's the wrong answer. That answer is not quite right. The reason it's not right is because it's counting everything twice, right? You could get the ace of hearts first and the king of diamonds second, or the king of diamonds first and the ace of hearts second, and those are being counted differently here. So we have to actually divide by 2, which is really 52 choose 2. There are 52 choose 2 ways of choosing 2 cards. I should say 52 distinct ways of picking 2 cards out of 52 cards. Okay, how many ways of getting what we want? this is where things are a little bit trickier. So I'm going to show you kind of the long way and then maybe the shorter way. So there's 4 different things that can happen. We can have diamonds, clubs, spades, or hearts. So how many ways are there getting 2 diamonds? Well, the first card could be a diamond. And the second card could be a diamond. But I'm overcounting, right? This could be ace of diamonds, king of diamonds, or king of diamonds, ace of diamonds. So really, that's the number of ways of getting 2 diamonds. And then here's the number of ways of getting 2 clubs. And here's the number of ways of getting 2 hearts. And here's the number of ways of getting 2 spades. So I can count this up, right? This is going to be, right, 13 choose, I mean, this is just 4 times 13 choose 2. So here's the way I really would have liked to imagine it. I kind of go through an order and think about what do I need to pick in kind of in the context of the problem. In this case, I'm trying to get 2 cards of the same suit. So I need to pick the suit. How many ways are there picking the suit? There's 4 choose 1 ways of picking 1 suit out of 4 suits, which is 4. I know it seems dumb to say it kind of, but like, it's true. Now that you picked your suit, you have to pick 2 cards out of the 13 cards in that suit, out of the 13 ranks in that suit. Well, there's exactly 13 choose 2 ways of doing that. So to answer our question, our probability would be this number divided by that number. 4 choose 1 times 13 choose 2 over 50 choose 2. Which I would probably leave as is unless I needed to simplify. Now we can't simplify. And actually the simplifying here isn't terrible if we think about it, right? 4 choose 1 is just 4. 13 choose 2 is 13 times 12 over 2. 52 choose 2 is 52 times 51 over 2. These 2's cancel. 4 times 13 is 52, so 4 times 13 and 52 cancel. And so it ends up being 12 out of 51. Which seems strangely simple, right? Like I didn't expect it to be such a nice number, but I guess that was so wow, that's actually kind of cool. That makes total sense to me. Here's why. Pick any one card, right? So the first card is picked, it has a suit, right? And then the next card, there's 51 cards left to pick from. 12 of those are the same suit. There's a 12 out of 51 chance it's the same suit. So that's a totally different way you can get to the same answer. Great. So I do want to talk very, very briefly. So one of the homework problems he asks, the one that asks is about the probability of getting 2 of a kind, 2 pairs, I'm sorry. And I want to kind of discuss that versus, so there's kind of a weird thing. We're talking about 2 pair versus a full house. So let's talk about the full house first of all. So full house, which is 3 of one kind and 2 of another kind. For example, 3 sevens and 2 aces. That would be a full house. 7s over aces, or 7s full of aces. Whereas 2 pair could be like 2 sevens, 2 aces, and one other card that's neither of those, like a jack, for example. Okay, so how am I going to calculate this probability? Well, I need to do things in the right order. First, I need to pick the ranks, right? There's lots of different ways you could have a full house. You could have 3 aces and 2 kings. You could have 3 aces and 2 jacks. You could have 3 aces, right? There's a lot of 3 aces. And then there's a lot of other 3s and 2s. So I have to first pick the ranks. And actually, this is the place where this question is different than this question. So when picking the ranks here, it matters which rank is which, right? One of them is going to be a 3 of a kind, and one of them is going to be a 2 of a kind, or a pair. So I'm going to pick out of my 13 ranks, I'm going to choose one of them to be the 3 of a kind. And then after I pick this one to be the 3 of a kind, I have to choose 3 of those cards out of the 4 of them that there are. So this is the number of ways of picking 3 of a kind, which is 13 times 4, which is 52. So there's actually 52 different ways you can pick 3 of a kind in a deck. You can pick any rank, and then from any rank, there are 4 different ways of picking 3 of a kind in each rank, excluding 1 card each time. And then for the 2 of a kind, well, it has to be a different rank, right? I can't pick 2 of a kind from a card I've already picked 3 of a kind from. There aren't enough cards left. So from the 12 remaining ranks, I pick 1 rank. And then from whatever card I've picked in that rank, let's say they're 9s, I'm going to pick 2 of the 9s out of the 4 of them. And there are exactly 4 choose 2 ways of doing that. Okay, and then, okay, this other problem is different. And here's how it's different. It's not going to be 13 choose 1 times 4 choose 2 times 12 choose 1 times 4 choose 2 times 11 choose 1 times 4 choose 1 out of this. This is almost right, but not quite. So here's what I've done. I've picked, say, aces or 7s, and then picked 2 of them. And then I picked aces, and then I picked 2 of them. And then I picked something that wasn't 7s or aces, which there's 11 of left. And then out of the 4 of them, I picked 1 of them. Now, the problem with the way I've done this here is picking 7s first and aces second, or aces first and 7s second, are getting counted differently. Which doesn't matter here because it is different if you have 3 aces and 2 7s or 3 7s and 2 aces. But it's not different if you have 2 aces and 2 7s or 2 7s and 2 aces. So in this case, we have to do this instead, which is just slightly different. It's going to be 13 choose 2. Out of the 13 ranks, you want to pick 2 of them. And there's 13 choose 2 ways of doing that. And 13 choose 2 is 13 times 12 over 2, which is 13 times 6, which is 78. Whereas 13 choose 1 times 12 choose 1 is 13 times 12, which is 150. Is that right? Sorry, now I'm like, is my math right? 13 times 12 is, wow, a number I used to know once upon a time, 156. Yeah, okay. So, right, so this would be twice as big as it needs to be. This would be 156. So it's actually going to be 13 choose 2 times 4 choose 2 times 4 choose 2. So this is the number of ways of getting 2 pairs. Pick 2 ranks, 2 of the first rank, 2 of the second rank. And then you still have to pick the 5th rank here, or the 5th card out of the remaining 11 ranks, and then choose 1 of them out of 4. So this is actually how you pick 2 pairs. It's a little bit different than how you pick a full house. And it's definitely something that has come up before in the past. So something to be aware of. All right, I think we're out of time. Let me know what you guys want to see on Wednesday. And I think a couple of you all have a test coming up. Is that correct? Let's see. Yeah, Carlson had a test. Sorry. Or no, you guys said it got pushed back, right? Carlson people, anybody? I think the Carlson test got pushed back to test as, right now. Okay. Well, hopefully it's going well. If you have questions, you're welcome to shoot me an email and I will try to answer them vaguely, but somewhat helpfully, although not inappropriately. And yeah, Rademacher's test is supposed to be this Friday. So, all right, we'll try and see. We'll see what we can do as far as getting ready for the Rademacher test on Friday. And to the Carlson people, best of luck. All right, that's all I got for you guys today. Take care. I'll see you on Wednesday. You're all welcome, as usual.